In any event, tonight our speaker is Dan Lane, ADOCY. He's from the Deep Space Exploration Society, known by the acronym DSES, and he's, I guess, the science lead. He's going to talk to us about amateur radio astronomy, including their telescope, the radio telescope down near Haswell, Colorado. So without any more of an introduction than that, I'd like to introduce you to Dan Lane.
All right, thanks. Hopefully I can get the hang of just flipping slides. Like some of the rest of you, I'm kind of coming out of hibernation from this past long season. But so yeah, I live up in Larkspur, just north of here. I'm live in Douglas County, so I've been in Aries Deck and some of those things. And I'm going to talk about Deep Space Exploration Society and some amateur radio astronomy. I especially want to thank Ray Uberecken on this list here, AA0L, Dr. Rich Russell, AC0UB, and Bill Miller, KC0FHN. Those three guys have really helped me kind of get up to speed on what's going on down there. And if you don't remember anything else at all tonight, just remember this website, dses.science. That's got all the information that we do and all the current stuff. So dses.science. And if you are interested in joining or anything like that, it's just information at dses.science. So the agenda, kind of what Lauren and Steve had asked me to kind of focus on. What is DSES and what in the world are we doing in Haswell? And where is Haswell? So Haswell, I've never heard of it. It's almost a ghost town, way down in southeast Colorado. It's about 2 hours and 15 minutes from here. It's flat, there's wheat fields and nothing else. The nearest town with any service is Eads, which is 30 miles away. So it's a relatively radio quiet zone. So I'll talk about what we're doing down there, and I'll talk about pulsars. Can amateurs actually detect pulsars? And the answer is yes. And then I'll talk about, whoops, I guess I'm supposed to stay over here. I'll talk about using the 60-foot dish down there for moonbounds. And I'm going to try and keep this at a high level. I don't want to do a deep dive down to any particular technical topic. I might be able to field some questions, but I certainly don't know everything about all these topics. And so it's going to be kind of a high level, broad brush. So I might be kind of covering lots of things at the top level, but not in great depth here. The charter, let's see, I've lost part of the slide here. What does that mean? I don't have the bottom part of the slide. I don't know how critical that is. There's another couple of lines here on all the slides. Oh, well, I might have to fake it. So at home, I do everything on Linux, and I have a different size screen. So it might just be the size of screen, but the slides would have a slide number and a little bit more, but I think we can get by without that. You guys know how to do business meetings. I've never seen officers elected that quick. Wow, that was impressive. So, yeah, I mean, the DSES is not unlike this. It's a group of volunteers, mainly hams, doing ham radio and amateur astronomy. The charter is, we're a nonprofit dedicated to practical radio astronomy, space science, and education, space education for students, for the general public and society members. So we really do try to do STEM events. We've helped judge science fairs, and one of our members teaches astronomy at Pikes Peak Community College. He brings students out now and then, so we really try and spread the knowledge. So we own and operate a 60-foot radio telescope near Haswell, Colorado. And the site is named, and just the bottom line just says it's the Paul Plishner Radio Astronomy and Space Sciences Center. And we'll come to that here in a minute. But that's a picture of the dish down there. The history, up on Table Mountain near Boulder, there's two 60-foot dishes, and there's an identical 60-foot dish down near Haswell. So the one on the right is Haswell. These two here are Table Mountain up near Boulder. These were originally built as part of a network of sites for the National Bureau of Standards. Now it's the National Institute of Standards and Technology. And their goal was to do tropospheric scatter propagation studies for the Air Force. And the Air Force did conduct those studies from 1958 to 1974 to learn more about how radio signals propagate through the troposphere. This is the original spec. Somebody took a picture of it and got it here. It's at the frequencies. The dish will operate from 400 megahertz to 2 gigahertz. It's 60-foot dish, a 42 dBi gain. The beam width at 1.2 gigahertz is 0.8 of a degree. So it's not a very big beam width at that frequency. It gives the noise, temperature, and figures, and it can cover the whole part of the sky. How did DSES come to be? Well, we have a debt of gratitude to folks in Boulder. DSES was originally formed in 1991 in Boulder to restore those twin 60-foot dishes there on Table Mountain. So those dishes up at Table Mountain had been sitting idle for 20 years, and some hams and people around Boulder got permission to restore them, and they did. And they had some good success. And about the same time that DSES formed, there was this kind of a splinter group, another group called EOSS. You've probably heard of them. It's the Edge of Space Sciences. They're the ones that launch weather balloons, and you can track them on APRS. So we'll have an APRS transponder on the weather balloon, and you can track it. And so EOSS started from some of the same people at the same time up in the Boulder area. I wonder. So yeah, I am missing part of it. And like I said, I think I didn't think of that when I came, is I might have to reformat them from a different size screen. But so after 9/11, hams lost access to Table Mountain. Table Mountain is a federal research site, the Site 22, T22. After 9/11, the attacks then, everything tightened down and clamped down. Hams lost access to that site. And so meanwhile, the Haswell site had been dormant from 1974 to 2009. Paul Plishner, he was a radar contractor in Boulder. He actually purchased the site at government auction. So you know how it is with the government. When the government is done with something, they have to wait 10 years, and then they can actually auction it off. I don't know what he got it for, but he never actually used it. And these guys in Boulder at DSES developed relations with him, and eventually he donated the site in Haswell to DSES. So DSES now owns that. It's the dish, and there's 5 acres there. And so what the Boulder group did, starting in about 2009, is they moved a comm trailer down there from Table Mountain, and it had equipment and gear, and they started refurbishing and restoring the dish in Haswell. And then, I think on this, there's a PDF on here that you can put on your computers, or you can read some of the other details later. So I'm going to talk about what's not shown on the slide, but the Boulder group started the restoration, and there was kind of a transition from Boulder to Colorado Springs as the Boulder group found out how far it is to drive down there. They would go down there and spend a weekend, but it's pretty rudimentary. We only got electricity a couple of years ago down there. The government ran it on generators. So the membership, but there were there was 3 people, especially key members, that they would spend weekends down there cleaning and getting the dust off and restoring that, and just rebuilding the whole thing. And they could do that because they had done it there for the Boulder dishes, so they kind of knew what to do because they're the same dish. As the membership kind of transitioned into Colorado Springs, then over the last 3 or 4 years, it's more members from Colorado Springs area than there are from other parts. And we got electricity in there. if you live in the country, you know that if you're past the end of the line, you get to pay to bring the line down. And that money was donated. I've got internet down there right now, and it's just DSL, the old style DSL, but that's what we have. They've installed a complete new dish control system. It was an analog system, which still works, but we now have a completely automated dish control system for tracking. So we can track in azimuth and elevation, and that's just based on a Raspberry Pi and a little Linux laptop. So it's all digital. And so they've been doing those upgrades and adding ham radio capabilities as well. So there's kind of a dual capability there. Radio astronomy and ham radio both take place down there. And so I think the last line on this slide, as I said, thanks for the countless volunteer hours that got the whole thing operational again. It is operational now. For a good part of this year, it was not, because some parts in the string for the control for the dish failed. There's no replacement, so the companies are long gone. So that's when they redid the whole thing in digital with the Raspberry Pi. But it's all working great now. The digital control system gives us about 1/10 of a degree of accuracy. So when we're pointing at something, the moon or a star, we're pointing at something, we're good to about 1/10 of a degree, and we can track that over hours. So that's kind of the background on DSES. Let me talk about radio astronomy. This top line just shows the wavelength and how opaque or how transparent the atmosphere is at different wavelengths. So here's the visible in the nanometer region. Here's the visible wavelengths that we all see in visible light. The atmosphere is opaque here. So if we want to do gamma ray, X-ray, ultraviolet astronomy, we launch satellites. You can't do it from the ground. From the ground, you can do visible. So you can have your optical telescope here at visible. Infrared is not too good. Most infrared telescopes are above the atmosphere. They're in low Earth orbit. This is the sweet spot for us. If we're doing ground-based radio astronomy with a telescope, this is where we operate in these wavelengths. And I think I say over there, it's roughly, it's just a rough number, 5 megahertz up to about 30 gigahertz, more or less, is the region where the atmosphere is transparent. So signals coming down don't get bounced off or deflected. We can actually receive them. Now, the radio waves, you already know this, the radio waves out here at 1 meter, 10 meters are much, much longer than the visible light wavelengths. So accordingly, a radio telescope must be much larger. That's why they build huge dishes or build interferometers where they connect together several dishes to do radio astronomy. And I don't think it shows on this little frequency on the band plan here, but it does show if you look at a bigger, like the IEEE frequency spectrum allocation chart, it'll show you all the frequencies that are allocated for radio and TV and commercial use and civil and military. And in there's little segments that are allocated for radio astronomy. Those are protected. Those specific frequencies are key ones, and we'll see some here later. Those are important for to protect them from RFI, radio frequency interference. So we have one of the same goals whenever you're using your ham radio. One of the things you want to do, you want to minimize RFI in your shack, and you want to maximize your signal noise ratio. Well, we do the same thing. We have to minimize the RFI and maximize the SNR. Yeah, this slide thing is interesting. So those two of them were chopped off, but these aren't. And I think now it's because I'm an amateur, especially when it comes to making PowerPoint slides. I think I had a different master slide on some of those, and it was goofy. So the radio signals that we're trying to detect are extremely weak. This chart shows comparison of the sun up at the top and some other signals. In radio astronomy, we measure something called flux density. Flux density is a measure of the signal strength. The units of flux density are Jansky. That's named after Karl Jansky. He's an early pioneer of radio astronomy. And so the units, 1 Jansky is 10 to the minus 26 watts per square meter per hertz. 10 to the minus 26, that's small, tiny. So this one single Jansky is a very weak signal to begin with. And this chart here is a logarithmic scale. So each side, X and Y, are logarithmic scale. So, this would be 1 down here, 10, 100, 1,000. In the middle are supernova remnants like Cassiopeia A, Cygnus A, Taurus A, some of those nebula that you see beautiful colored pictures of, the supernova remnants are in this range. Well, I'm interested in pulsars. Pulsars are off the chart. They're down here in the Millijansky range. So if this is 1, then the next one would be 0.1 and 0.01. So most pulsars are down in the Millijansky range. Pulsars are broadband emitters, so they'll cover a lot of these frequencies, but there's only a few bright ones that barely get up above the 1 Jansky range. Now, I want to talk about 3 projects you can try at home. You don't have to have a 60-foot dish. You don't have to drive to Haswell. These are the next 3 slides are projects that you can try at home. They're not that difficult, and it's a great way to get started if you're interested in radio astronomy. The first one is called Radio Jove, and the basic idea here is you can monitor radio storms on Jupiter. So Jupiter, no surprising, since it's the largest planet, it has, after the sun, it has the largest magnetic field. The magnetic field of Jupiter actually extends out almost to the orbit of Saturn. So it's a very large magnetic field there. And these radio emissions are in the HF band. So something that enhances these storms is Jupiter's moon Io. If you've ever looked at Jupiter in a telescope, sometimes you'll see the 4 moons that Galileo saw, or you'll see the shadows of the 4 big moons, but Io is one of the principal moons. It's when it goes by where some of these storms are, it increases the intensity of the storm. So Io's orbit is easy to predict, and that's what this software, it's from radiosky.com. They have software tools that simply predict the orbit of Io. That's well known. And as Io goes over certain spots on Jupiter, it enhances the radio emissions there from the magnetic storms, and then we can detect them. So for more project information, this is actually a NASA-sponsored project. NASA's been doing this for about 20 years. A lot of high school and college students get interested in doing it. The antenna, and it's exactly like ham radio, the antenna is it. The antenna is the main thing in all this stuff. So the antenna for Radio Jupiter is this dual dipole arrangement, and it's a half wavelength. We're operating at 20.1 megahertz, so roughly at 20 megahertz. We have one dipole here, another dipole, and they're pointing towards Jupiter. So you kind of point it towards the general region where Jupiter is in the plane of the ecliptic. And then you just run this, your coax in. Any SDR will work. We're using Flex right now, but any SDR will work. And so then you can visualize over there on the right, you can visualize the bursts that come from the storms on Jupiter. And there's basically 2 kinds. There's a long burst and a short burst, and you can visualize them. Or with a little sound card, you can listen to them. You can actually hear the crack, crackle, and pop, and then you'll hear the short burst or a long burst. So the way Jupiter's orbit is, for the last year or so, it's been fairly quiet. When it was closer to the sun, it's getting further away. We'll be able to detect these. So we're kind of moving into the season of listening to Jupiter's radio storms over the next year. And so they had one of these at Haswell before. It kind of fell into disrepair. Over the summer, we put up a new one. So we have a new antenna. We have a SDR down there. And now that we have internet, we're going to put this on our website. So it'll probably be early next year, but we'll have the software running on the website where anybody can log in and see something like that, or hopefully be able to listen to it as well. You don't have to drive down there. We can do things like this on internet. One thing we cannot do on internet is do remote control a big dish. The big dish is kind of special, and we have a 2-person rule. There always has to be 2 people there to operate it. You guys know what safety is, and because if something happens, if we lose that dish, then that's it. We can't build another one. So we cannot operate the big dish remotely, be moving it around. But we can do something like Radio Jupiter remotely, and we will be. So that'll be on the website. The second one is to monitor space weather. And so this one is called SID. It stands for Sudden Ionospheric Disturbance. And it's caused by solar flares. So the basic idea here is you're going to be monitoring the military VLF transmission. So the military worldwide, not just us, but worldwide, military uses very low frequency transmitters to communicate to the submarines underwater, because VLF goes through everything. So it's way down at 15 to 25 kilohertz. These transmitters are huge. I forget what the wavelength is there at VLF, but it's on the order of miles. So these are very long wavelengths. And you're just monitoring the carrier signal, much like if you're monitoring WWV during a solar eclipse or something like that. You're monitoring carrier. Down here on the right-hand corner, basically it's showing 1 day. So this chart shows 24-hour period, and the purple is the nighttime. When the sun comes out, you lose about half your signal strength. But then there's those 4 spikes there, and those were solar flares, 4 different solar flares that 1 day. The solar flares cause disruption in the ionosphere, which causes disruption in the propagation of these VLF signals, which you can monitor. And all that data goes to something called the Stanford Solar Center. Stanford collects this from monitors all over the world, 24/7, and then they can quickly correlate. And because the flare may appear stronger in different regions, so they can quickly correlate that, and it helps them predict the severity of a solar storm for protecting satellites and things like that. You can build an antenna very easily, or SARA. SARA is the Society for Amateur Radio Astronomers. It's kind of like a ARRL kind of thing, which is all amateurs. They actually sell a Super SID kit where you can make this, but the antenna itself is just this. You can use PVC or a wood frame. It's a wire frame. It's an open loop wire antenna. You just wrap the antenna wire around this loop a number of times, plug it into an SDR, and that's it. And because it's VLF, so one of the guys in our club, he has one of these mounted on his wall in his house, and he's porting data 24/7 to Stanford. So you don't have to put it outside in the rain. But that's an interesting, easy way to get started. And you don't have to go to Haswell for that. And the third one is neutral hydrogen. This is another project. You can do it at home. Hydrogen is the most abundant element in the universe. Neutral hydrogen, the neutral hydrogen gas is the main component of something we call the interstellar medium. So the medium between stars is not vacuum. Sometimes we think, oh, there's nothing in outer space. Outer space is full. It's packed with hydrogen gas, with some other molecules, and with dust. So there's these dust and hydrogen clouds floating around in between stars, and that's called the interstellar medium. And so we can observe this spectral line, and then we can use our observations to map the bright objects using either a small dish. It can be as small as about a 3 meter, about a 9-foot dish, or a horn antenna. Some people make a simple microwave horn antenna out of a coffee can or something like that. So it's not a big deal. So over here on the left, and sometimes I wonder, well, okay, neutral hydrogen, how can we pick that up on radio? So here's a picture of a neutral hydrogen atom. Hydrogen has 1 proton, 1 electron, no neutron. So that's it, a proton and an electron. And it's showing their spin orbit. Both of them have the upspin. They're both spinning in the same direction. Occasionally, the hydrogen atom will decay into its rest state. And when it does that, the electron flips. It's just called a spin-flip transition. And when it flips, it emits a photon. Well, that photon is at a wavelength of 21 centimeters. 21 centimeter photon is 1420.4 megahertz. So that's why 1420 is one of those protected regions in the spectrum, because radio astronomers do a lot of work at 1420. So that part of the spectrum is protected. The map over on the right was done by professional astronomers, but it's showing what the whole sky looks like at 21 centimeters. Instead of seeing through visible light, if you saw at 21 centimeters, that's what the whole sky looks like. The bright band in the middle is the Milky Way. The bright splotches down on the right, well, that's the clouds of Magellan, the large and small cloud of Magellan. Those are nearby dwarf galaxies that you can see from the southern hemisphere. We don't see them from here. So with a relatively small dish and an SDR, you can do some hydrogen at home. So those are three kind of starter projects. Then for hydrogen, I do want to show, here's an observation that we did just a couple of months ago of an object called S7. So it's not like Cassiopeia or something. That's its name is S7. It's a stable, bright hydrogen emitter. We use it for calibration. So we have to calibrate the radio telescope so that we can prove that we, if we claim we see something, we want to be able to prove it. So we have to calibrate the telescope. And this is one of the objects we use to try and calibrate. We took this on August 7th, a 60-foot dish. It was using the 1420 megahertz feed. And I'll talk more about this LNA. So up in the feed horn, we have LNA. LNA is a low noise amplifier. You can just think of it like a preamp. It's a low noise amplifier. So we want to amplify the signal by 20 or 30 dB or something like that, so we can get it down to coax, but it has to be low noise. And then it's usually followed by a bandpass filter. We just want a certain segment with 100 megahertz or something. Then the receiver, I used an AirSpy, a simple AirSpy R2. We use a GPS disciplined oscillator because we want the clock working right. So we use GPS on it. I had it set at 2.5 megahertz bandwidth, and I integrated for 2 minutes, which means we're tracking for 2 minutes this object. We're just collecting 2 minutes worth of data. So it's not an instant snapshot like you do with your camera at the optical region. When you're doing radio astronomy, you're collecting photons over time, and then you're integrating. This ran on a laptop. It ran on my laptop sitting in that bag. It's a System 76 laptop. I run Ubuntu. We use GNU Radio and Python and a package called Astro Virgo to do some of the heavy lifting. So I don't have to worry about coordinate conversions and all the things that go on behind the scenes in software. There's a lot of software available that's done. You just plug it in and go. Now, speaking in terms of science, if I'm down there at Haswell, there's about 100 things that can go wrong, and usually do go wrong when you're trying to get something going. It's a complex processing chain, and I'm fairly new at this, and I want to know if what I'm seeing on the screen is real or if it's noise or RFI or what is it. So what I do is I use tools to predict what I'm going to see. The LAB hydrogen survey, LAB was 3 radio telescopes across the world. They did a hydrogen survey. They spent 2 years doing it, collecting tons of data. And then they generated a website and some tools so that you just I tell this tool the direction I'm pointing. I'm going to be pointing towards S7. I tell it my beam width, and it tells me what I should expect to see. So I expect to see these 3 spikes. So then when I go run my software and collect some data, I can reduce it down to this. And for me, that's good. That's great. Yeah, the noise floor is at a different level, but I'm interested in the peaks, and the peaks are great. And most importantly, they line up well on this red dashed line. The red dashed line is 21 centimeters. That's 1420.4. That's the rest frequency of hydrogen. Well, we all know that every single thing in our galaxy and in the universe is moving around. Some of them are moving very quickly. So there's several Doppler shifts that you have to account for when you're doing the spectrum. I can't just take the initial. So the initial picture, it's shifted way over here. I have to account for the Doppler shifts because the Earth is rotating, the solar system is moving through this arm of the galaxy's moving. All those things are accounted for in order to get it lined up right for Doppler shift. I also have to calibrate it for background because what we do is we look at dark sky. We look at a part of the sky where there's absolutely nothing. And then we look over at our target and we can subtract out that background, get rid of noise. So that's how we calibrate it. The very far right picture is just, that's again, the Milky Way. That's the hydrogen line for the Milky Way. It looks, like that smile because it's in, the coordinates are right ascension and declination. So right ascension and declination are kind of like azimuth and elevation. Tells you which way right or left to point and which way up and down to point. I like to know where it is in relation to the Milky Way. Anyway, that's something we did with hydrogen there. So let me talk about pulsars. This is how we detect pulsars. I want to clarify, we're not searching for new pulsars. Searching for a blind search is a couple of magnitudes harder than anything we're doing. And what we're doing is hard enough already. So what we're doing is detecting known pulsars. The scientists and astronomers that have found them, then they publish the results. So it's easy to look up, to find the specifics of a pulsar. It's position, the pulse frequency, the brightness, and things like that. A pulsar is kind of like a lighthouse where it's lights flashing. If you're looking in the right way, you'd see it. So this pulse, if it's pulsating towards the Earth, then we get that pulse. On the dish, we have a feed horn. It's a parabolic dish. The feed horn is at the focal point. In the feed horn itself, that's where the antenna is, inside the feed horn. The antenna is not the dish. The dish is just a reflector. The antenna itself in this feed horn is a simple little quarter wavelength dipole. And at the frequency we're operating at just a couple of inches. So you look in the feed horn, there's this tiny little wire. That's where the magic happens. That's where the photons hit and get converted to electrons flowing down the wire, and then we can measure a little voltage. And so we have that low noise amplifier. There's 4 different feed horns. We use different feed horns for different frequencies. 3 of them come down on coax, it's helix coax, and 1 of them comes down on fiber. The SDR we'll talk about later, but there's just basically an SDR to do the recording. And then we have a computer to do the data analysis, to actually produce some plots. We get these pulses. There's a completely separate dish control system that I mentioned earlier, and it's on its own little network. That's the Linux laptop with a Raspberry Pi up in the pedestal that does the pointing and tracking. So that's kind of an overview of the components. You might be asking, well, what's a pulsar? And scientists don't really know completely. It's new. It's not totally understood. A pulsar was first discovered completely by chance. It was unexpected by Jocelyn Bell in 1967. She was a graduate student at Cambridge in England, and she was doing some radio astronomy experiments, and she started noticing this anomaly. Well, it turns out the anomaly was a pulsar, and that's how it was first detected. There's about 2,500 of them that are known now. Most of them are very weak, but there's some bright ones. A pulsar is this little thing right here. It's a neutron star. A neutron star is a collapsed core from a supernova explosion. So if a star is large enough, if it goes supernova, blows off its outer shells, what's left is this neutron star, which is a very compact star. Because it's so small, it's rapidly spinning, it's highly magnetized, and the magnetic fields that are shown here is the source of the pulse that we see. So it's not generally not in the visible light wavelengths, it's in the radio waves. They're up in the gamma rays and X-rays as well. The spin periods run from a few milliseconds up to a few seconds. They're very precise. They're being used as very precise clocks. They're being used to actually find and detect gravitational waves and things like that. They're very precise, but the pulse features vary. Not only do the pulse features vary from one pulsar to the next, the actual pulse itself can vary from one pulse to the next. So if you're looking at one pulsar, the pulse features, its strength and some of the shape, some nodes on it can change. Part of that is, I think, the physical change within the magnetic field. Part of it is and it doesn't quite show up here, is we're back to the interstellar medium. The interstellar medium is all this hydrogen gas and dust, and these radio waves have to go through all that to get here. And so it's called dispersion. The broadband signal from a pulsar, the lower frequencies arrive first, then a little bit quicker than the higher frequencies. So it spreads out and disperses the pulse. We have to account for that dispersion. But that dispersion helps us understand how far away that pulsar might be and some of its characteristics. Crab Nebula is one of my favorites. So this is a supernova remnant. This is the one that was observed in 1054. So astronomers in China and other places noted that down. Bright star appeared for a while and then disappeared. Well, this is what we see today, 1,000 years, not quite 1,000 years later. So the actual Crab pulsar, so this is a supernova remnant, but right in the center of that red star, that's a pulsar. So the Crab, besides being a nebula, it's also a pulsar. This is one, there's only 2 or 3 of them that are close enough and strong enough that astronomers have been able to identify an optical counterpart. What that means is the red star in the center is sending out pulses at visible length and also at radio and gamma ray frequency. So they've been able to correlate that. It's fairly fast, 33 millisecond. This very nice image was from the optical in red. It was from Hubble Space Telescope, and in blue is the X-ray components from the Chandra Space Telescope. So I'm going to just spend digital signal processing. Some of your radios do that. Your SDRs do it. We have to do it. And we use something called folding. The top line just shows noise. Just imagine a strip chart. So this is a time series, just noise, just a strip chart. You wouldn't know there's a pulsar signal in there because it looks like noise. So what the clever scientists have figured out is this concept called folding. If we know what the period of the pulsar is, then we're going to take this paper strip and fold it. Let's say it's 1 second. Then every 1 second where those marks are, we're going to fold that paper up and stack the paper up. And that's what's shown on the bottom. You stack the paper up and then look down. Well, you're going to be adding up all the small contributions from the real signal, and then the pulse at the bottom, it will stand out. So this is one way of increasing the signal noise ratio, is do this folding. When you have a whole lot of data, you don't see anything in it, well, you can actually, if you know what that period is, which that's why we're detecting known ones. This illustration is in the time domain. All of the calculations are done in the frequency domain. Everything's done with Fourier transforms into the frequency domain for efficiency. So, and this is a really busy chart, and I'm just going to go over it quickly. The cumulative folding idea. So if we're doing pulsar collection down there, sometimes we don't get anything. Could be all kinds of reasons, and you have to work on it, and sometimes you do. So, but the first iteration, this just looks like noise. And when you look at all the various, this is a professional software suite called Presto, what we use for verifying a pulsar. But first iteration, it's just noise. The second iteration, we've doubled the time period. Well, a peak jumped out. So this is what the folding does. The peak will start, the pulse will jump out, and you can faintly see there might be a line in here. So this plot here is phase versus time. This plot here is phase versus frequency. So we look at the phase information, the phase plots, to see if there's a pulse in there. And on the far right one, you can see, yeah. So that's the final one. That's considered a good profile. It may look like a mystery, but that's considered a good profile. All the numbers, all the different aspects, the period, the dispersion, all those things have to line up. So just kind of give you an idea of some of what we do there. And so the question, can amateurs detect pulsars? Well, yes, or I wouldn't be here. They have detected them just using moon bounce equipment, EME. So some people have used a 3 meter dish with AirSpy SDR. A guy in Italy has used a twin 23 element Yagi, which is EME equipment, with an RTL SDR, the little dongles that you can use. But if you're using a smaller antenna, then you have to track a lot longer. You track for hours. They'll track for 8 hours or something. They have to be able to track the pulsar across the sky and then integrate all that data. The best frequencies, and I mentioned that we have different feed horns for these different frequencies. We use 70 centimeters, 23 centimeters, and 21 centimeters are the three we use. We've detected 15. DSES has really only been online about an hour, a year and a half, and part of that time was lost. So they just really got started in 2020. So there's 15 unique pulsars they've been able to detect. And some of the pulsars we've detected multiple times. So amateur radio astronomers anyway are very much like hams. We like contests. So there's actually a ranking of, well, how many pulsars have you collected? And then, these guys in Germany, how many have you got? So we're fourth in the world. So we're happy about that. Some of them have actually detected around 50 pulsars. The top one has got about 50. So we have a ways to go. With the 60-foot dish, we don't have to track near as long. We can pick up pulsars, bright ones, in 5 or 10 minutes. Some of them will track for a half hour. We use a hardware simulator. It's an actual pulsar simulator. I used it a lot to learn how to run the software because you got these pulses. And I don't know what to do with this software. So Ray, AA0L, built this simulator. That's a handy club tool we have to learn how to deal with pulsars. The tools for the SDR, we use the USRP family. These were donated. We have a B210, which operates at 56 megahertz bandwidth, and we have an N210 at 10 megahertz. So these are similar to AirSpy. They just have broader bandwidth and a little bit higher sensitivity. The computer, we have a System 76. It's a 16-core dual thread, so it looks like 32 CPUs, 64 gigs of RAM. Again, it runs Ubuntu. The tools we use, I0NAA is a ham in Italy. He's developed this tool called Murmur, which uses a pulsar database to predict pulsar locations. And so we can actually plan ahead of time. We can look on the software and decide before we go down there, here's a half a dozen pulsars we're going to try. We have them rank ordered. I talked about this dish control system. We have to first get the dish pointed at the pulsar. And pulsars, you can track them night or day. The first time I went down to Haswell, I didn't know the difference. I was shocked they were down there working on pulsars in the day. I thought, what? Yeah, so day or night, it doesn't matter. As long as you're away from the sun. You can't be pointing near the sun, but if you're away from the sun, you'll see the pulsar day or night. We have an HP spectrum analyzer. We have a software spectrum analyzer. That's to calibrate the gains and to look for RFI. We use GNU radio. Our data is generated it's called filter bank, and it's just the frequency data instead of the time data. Presto, I showed you that one plot. That does all the heavy lifting, all the calculations. Presto uses a package called Tempo for timing analysis. We also use something called PSR Cat, which is a pulsar catalog. Basically, that's the ephemeris. And ephemeris is like a table that tells you where something is. You can have an ephemeris for the moon or anything. We have an ephemeris for the pulsar. It tells us where the pulsar is, when it rises, when it goes down, and even more importantly, it tells us the pulse period. It tells us what the period is. It tells us when the pulse will be pointing towards Earth, so we can do the timing analysis to get that. So these software tools either they're freely available on internet. You don't have to pay for them. But these are the ones that the professionals use. And so some of the amateurs are using the same ones just so we can prove that we actually got a pulsar. Here's an example of that one we just got a couple of months ago. The name of the pulsar is B2021 plus 51. That's just kind of its location. This shows the pulse, and the noise floor is down here. You get a good pulse. You can see its profile here in the phase plots. All the numbers look good. This was a 30-minute collect at 1420 megahertz. The period of this pulsar is about a half a second, 500 and some milliseconds. Flux density, 27 millijanskys, way under 1 Jansky. So it's a weak one, but 30 minutes, we got it. And I know the first time I looked at this chart, I thought, wow, you got a pulsar here. But actually, that's not a pulsar. It would be nice if I could say, yeah, that's what a pulsar looks like, but that's not what it looks like. This is just a two-dimensional plot of these two plots. So this is showing the period and the rate of change in 2 dimensions because you want the whole thing to converge. If you're iterating many, many times, you want that to converge there. So the final topic is moon bounce. The basic idea here is you have a transmitter on one side of the Earth, a receiver on the other side of the Earth on one somewhere. They both have to see the moon at the same time. The moon itself is not a very good radio reflector. It's not especially good. So you need fairly strong signal because you got to bounce it off the moon. You're going to lose quite a bit just getting there. And then on the receiving side. So the way it works for here in Colorado, when the moon first comes up, we can actually get signals from Belgium and from Europe. So when the moon first comes up, you can communicate moon bounce with folks in Europe. Then as the moon comes over the ocean, then you can do the East Coast. When it's overhead, you can do all the central United States, and then later the West Coast. And as it sets, you can still get Japan and Philippines and things like that. So I'll talk a little bit about moon bounce and some of the ham radio stuff we do down there. On the right side is our QSL card. So we send that out for contests or contacts, just to sample the QSL card. Our club station name is K0PRT. That's named after Paul Plishner, the guy that donated the whole equipment, but it's the Plishner Radio Telescope, K0PRT. So what do we have down there for ham radio? Here's a picture in the evening. Some of the ham antennas. There's a tri-band. It has 10, 15, and 20 meters. It's a Yagi on a 50-foot tower, which blows down about once a year, and we have to put it back up. It's very windy out there. We have a 5-band trap. There's dipoles for 80 and 160 meters, 3-element Yagi for 6 meters, and then there's a vertical for VHF that we just put up on the 50-foot tower, and that's kind of like what you guys do for call-in. So when we're driving out there, your cell phone doesn't work. You want to know if somebody's there, you can get on your handheld and just call in on the VHF. And the 60-foot dish when used for ham radio. Now, what's really interesting is, I'll tell you what, they knew how to build things in the 50s and 60s. This, I've been up in here, it's just solid steel. It's like being in the middle of a ship. This thing will never move. And it's got a huge concrete foundation. It's very well built. We always stow it in this position so it doesn't blow away. But the government built an underground bunker. So this little light down here, that's going down into the underground bunker. It's a concrete bunker because the workers and staff stayed there. And there's nothing else out there and nothing nearby. So we still use that bunker. There's actual bunk beds in there. There's, we got a microwave and refrigerator and things like that. But I just found that fascinating. And here's the ham shack. It looks like any other ham shack, just a table, some radios and notebooks on it. But these are donated radios. Some of the people that tend to go down there and do the ham radio are folks that live here in the Springs, but maybe they live in an apartment or they can't put up an antenna in their backyard because of restrictions. They love going down here because you can do whatever you want. There's all the antennas there already. There's the radios. And so they'll go down there and just do ham radio, DX, or they'll do contests using the stuff that's already just sitting there. Gary, W0TLM, he provided some of the photos and information in this section. He's also our webmaster. Any club's got to have a webmaster. So he kind of maintains our website. Now, for moon bounce, that's where we do ham radio with the 60-foot dish. And I have not actually done it yet. Last year was the first year they were able to get on the moon and do it. I hope to be able to do it this year. So last year they used an FT 736 in the trailer. This year we have an ICOM in there. Last year during the contest, they made contacts on CW phone and on JT65C. So many of you, I'm sure, used FT8, you've used Whisper, you've looked at WhisperNet and some of those digital modes out of the package WSJT-X. They provide all those digital modes. Well, included in those digital modes is something called JT65C. It's kind of like a Whisper mode, but it's for moon bounce. And that's what they used last year. If you use WSJT-X, you know that a couple times a year they come out with a new version. Everything changes a little bit. It's always slightly better. You can go a little bit lower noise. Anyway, they have a new version this year called Q65 for propagation for moon bounce and things like that. So that's what we'll be trying. In order to do moon bounce, we do it on 1296 megahertz. We have a 1296 feed that actually it's called a septum feed, but there's kind of two channels in it. You look in it and you see the two little dipoles and the two coax coming out. So one side's transmit, the other side's receive. So that's how we can transmit with this big dish. We've put the feed in there to get it set up for the upcoming ARRL EME contest, which they do every year about this time, October, November, December. This year, it's going to be November 19th and 20th, which is this weekend. Unfortunately for us in Colorado, it's during the full moon, which means you're up all night. So because it's a worldwide contest, everybody's doing it at the same time. It starts at midnight UTC, which is like 6 o'clock for us. Well, it's full moon, so we're going to be up. The ones that are down there will be up all night in the trailer. We do have heaters. We welcome guests and visitors all the time. We're kind of like you guys. You always want new blood to come in and help us. If you like to build things or like to do ham radio, we'd be glad to have you jump in. So the first part of the contest for us, it'll be this weekend and then again in December during full moon. I've been down there with Ray Uberecken the last 3 Saturdays. We've been troubleshooting the feed horn there. We took apart coax in here, trying to find, do we have problems with coax? What was wrong? Because we weren't getting signal out. We weren't getting signal out at all. And we had recently put in this 200-watt amp up in the feed horn. For the transmit side, there's also a 30 dB preamp for the receive side. Turns out neither one of those were working. They were working, but just barely. So last Saturday, we pulled them down, and Ray's got them in his house right now, trying to figure out what's wrong with them, and we'll get those fixed. So Ray's planning on putting those, the amps back in the feed horn up here on Friday afternoon. Then the contest starts. So you know how that goes if you're getting ready for a contest. Things don't work right. But it's interesting. So we have a 200-watt amp up there at the feed horn, and it's at that focal point of this 60-foot dish, and we saw the gain. So when you multiply the gain, we're actually putting out a few megawatts. So I have not participated in this yet. I hope to. But if you like to be on the receiving end of a pileup, this is one to do because this attracts a crowd. This is larger than most of the other EME groups, so we get all over the world, and it does get busy at times. But in this case, we're kind of sorting out who we can respond to instead of trying to break into the pileup, which I haven't been able to do yet. So, like I said, I haven't said that yet. Last year they did 4th. Last year was the very first year that DSES actually got on the moon. They tried the year before, too many problems. So they got on the moon last year. They were only on the moon part of the time. They couldn't be on all 4 days of that weekend or nights because, well, it's complex. There's a lot going on. The moon, it appears to us the moon is moving, but actually we're rotating quite quickly, and that induces a Doppler shift. And the Doppler shift varies coming and going depending on, is the moon rising, is it at zenith, or is it setting? So you have to account for the Doppler shift. You have to account for fading of the signals. And the signal can tend to be polarized in a circular polarization. If the moon is straight overhead and you just want to test, just key it up, speak into it, and see if it's working. The delay is 2.5 seconds to hear yourself. So it takes 2.5 seconds for the radio waves to go to the moon and bounce back. That's just the sheer distance it is to the moon. But I think it'll be a blast. We're trying to get get the gear back in place. We always welcome visitors and guests. Like I said, just go to dses.science, send them an email, and they'll help you with the particulars, or contact me. But you're welcome to come down to this event or other things. You know, if you're interested in ham radio, there's all the ham radio stuff. If you're interested in radio astronomy, there's some of the things we talked about there. And questions, that's it. Any questions about some of these things or?
Wow.
Yeah, Lauren?
I'm going to speculate about something.
Mhm.
You mentioned the WSJTX. Joe Taylor, one of the co-developers of that, won a Nobel Prize in science or in astronomy for his pulsar work.
Mhm.
I'm kind of speculating that WSJTX in the digital signal processing is kind of similar to that folding technique that was done to pull those weak signals and do detection.
So you're exactly right.
In that software.
You're exactly right. So Joe Taylor, he got his, so he's a professor of physics at Princeton. He did his work he was the first one to discover a binary pulsar and got a Nobel Prize for it. He used the Arecibo telescope. I don't remember when, it was in the 70s or 80s. I don't remember when, but he was using the Arecibo telescope in Puerto Rico, that great big one, and he detected the pulsars. And he wrote a lot of the software to do that, including the folding. And we're using a Presto package now to do the folding. The package that he originally wrote is called Tempo, and he wrote it in Fortran. You know, anybody remember Fortran?
Yeah.
Well, if you know, I don't know if you recall, this is a quiz, but on the one slide where I showed the software tools, I had Presto and then I had Tempo was one of the tools. That's Joe Taylor's product. It's still the Fortran tool he wrote is still the one in use because it's so tight. It's tight code. There's no comments. You know, so that's still in use. You know, that's the same Joe Taylor, and he's a ham, and he provides us with all these tools too.
So if you're doing digital FT8 or JT65,
Mhm.
you're doing similar
Yeah.
processing that's being done in
Yeah.
pulsar detection. The
He,
other thing that struck me is you mentioned in the horn, the actual antenna
Mhm.
on the dish, you said photons hitting the little wire.
yeah,
And when I think about radio, I think about electromagnetic waves. I don't think about it in terms of a photon. There seemed to be a lot of overlap between optical type of astronomy and radio type of astronomy when you start talking photons. So it struck me as interesting and a little confusing when you use that terminology.
so that's something I've just learned in the past year or so, because I was kind of the same. You know, when you think of visible light, you're thinking photons. You're thinking of EM, radio waves, you're thinking nice, you know, waves. But when you talk to a physicist, they'll say, no, it's all the same. They'll say, it doesn't matter whether you're looking at visible light, X-ray, gamma ray, you know, VLF, radio waves, it's all the same. And I heard a physicist say it like this. He said, the electromagnetic signals travel like a wave and hit like a photon. And so it doesn't matter if we're talking about visible light photons, radio frequency photons behave exactly the same. And so they will say, yeah, this hydrogen atom emitted a 21 centimeter photon. And really we're thinking, well, it's actually a wave, but yeah, it's the photon and the wave. Good point. It's, I guess it depends on which generation you were, you know, which textbook you read. Well,
Yeah, I think they call it wave particle duality.
that's exactly it. Yep.
They have attributes of both, and if you think about it real hard, my head usually just hurts.
Yeah.
Because there are experiments you can show there's clearly a particle, and then there's experiments where you can show the wave interaction. You
Yeah.
go, well, how does that work?
Yeah, it's kind of boggles the common sense, but that's exactly right. It's the wave particle duality.
So the Table Mountain 2 dishes, are they still up there?
They're still there. They're not operational. They're just sitting there, but nobody can access them. So I don't know why, they closed off all kinds of things after 9/11, and some things haven't opened up since then. I think they found it convenient.
How many weekends out of a month are people typically down there? You mentioned you've been down there at Haswell the past 3 Saturdays. Is it pretty active throughout the year?
Certain times of the year, there's I think that there's around 50 or 60 members in DSES, but like most volunteer clubs, there's the number of active ones is much smaller. And many of the members, there's a guy who lives in Montana, somebody in California, they got involved. And especially during COVID, they could stay on the Zoom meetings and things, but they're not here to be active. So it's a smaller group that are active. And what we try to do is every 3rd Saturday have a work day. There's endless projects and work things to do, cleaning or repairing and all that. So half a dozen might be down there on a work day. Then there's other times when, like during a contest, or if you're looking for pulsars, you can go any day of the week. You can go down on a different day, but probably on average, I'd say there's somebody there only about 3-4 times a month, maybe once a week or so. I mentioned that dish control system for the tracking and pointing. That's there's 3 guys that did all that software. It's world-class software that they built just for this system. It has all the maps, the coordinate conversions, the controls. They tend to go down there during the week, but they've done an excellent job, and they're still working on refining it. Well, they all 3 worked together at Northrop Grumman. They all worked on GEOS, which is another optical tracking system, and they're retired, and they're still doing the same thing they used to do and loving it. So, yeah, it's a smaller group that are active, but we're hoping to get, like, if we get Radio Jove online, I think that'll increase some of the presence and things. But
so, where a lot of the work you're doing is just kind of reinforcing stuff that's already been done, related to pulsar or Jove. How important is that as science? Is it reinforcing anything? Are there new discoveries that are potentially coming out of that work, or just how does it fit in?
So in terms of science that we can do, there's, to me, there's some very interesting aspects of pulsars. So think of this pulsar as this rapidly spinning, very compact star. Well, we know from angular momentum, it's going to be slowing down. And so the pulse that we see, even though I said it's a very precise clock, it is. We also know from the physical properties that we can measure that it's slowing down. We know what the spin down rate is, called the spin down rate. We know what that is, and we can monitor that to see if there's changes or things. So that's one thing we can do, is just monitor and predict the spin down rate, and then go back, say once a year, and do the same observation on the same pulsar with the same equipment, and see what you have. There's another pulsar, actually the crab one that I showed a picture of, the crab pulsar. They all tend to have this one nice peak pulse. The crab has a secondary pulse, which is much smaller, but you can pick it up. So it actually has 2 pulses, and they're not sure of all the physics involved in that. It's still new. They're trying to sort it out. But the crab also has something called a giant pulse, and it's random. It'll be a couple of times an hour. There'll just be a giant pulse, a big pulse, unrelated to the regular period pulses. And so those are things that we can detect. The group I mentioned called SARA, the Society of Amateur Radio Astronomers, they do publish a journal every other month. They have conferences. They'll go to the Green Bank Observatory, or they'll go down to New Mexico to visit that very large array. They publish papers that are peer-reviewed, at least within the community. So I don't know if you've ever heard of FRB, a fast radio burst. So that's something that just popped up in the last couple of years. They've started seeing these. They'll be looking out in some direction, and all of a sudden they'll just get this burst of energy, very large burst of energy, just in a tiny fraction of a second, it's gone. Well, some of these FRBs have started repeating. And so there's a radio telescope in Canada that tries to monitor these. And if they pick up one of the repeaters starting up again, then they'll put out a telegram. It's called an astronomer's telegram. It goes out worldwide. It alerts the astronomers to some event. And there's an amateur astronomy group in Germany that have a dish larger than ours, and they have a lot of nice modern equipment that we don't have. They actually detected the FRB, the very first amateur group in the world to do that. And so it actually went into the astronomer's telegram, and they congratulate them. Yeah, but that's a case of an amateur group. It's just a bunch of retired Germans, but they have this nice gear, and they detected this FRB, the first one ever. It took them many hours and lots of tries, but they were able to do that. So that adds to the science base. Every time somebody collects a pulsar, you note the characteristics, it goes into the database, and then later, graduate students have to go through it and sort it out.
I'd like to point out, Dan is here because one of the members of our club last month, kind of randomly in discussion, Steve Plosky, is actually the trustee of K0PRT, so a member of our club, and introduced me to Dan. So, when we get a chance, we want to thank Steve for the introduction.
Yep, Steve was not able to be here tonight. He's been president of DSES, and he's very knowledgeable and helped. One of the feed horns that we used is one that he made. Guys that like to do our RF engineering or build feed horns, we'll put them up there and try them.
The JPL Deep Space Tracking Network has a whole different reason for existence. They're looking at Voyager and all these people. But when I visited, I remember a raw sensitivity before digital signal processing about a little south of about -150. Mm-hmm. Is that sort of the range you can get out of your 60-foot dish? Because JPL's working with 85-foot dishes.
Right. We have not tried that. We've talked about it. We know we can get the geosync satellites. We've talked about using geosync satellites for calibrating because they're, you know where they are and you know their signals. We have not tried tracking some of those. I think that's Goldstone and some of those that do the tracking. Yeah, so we have not tried that. I don't know that we'd be able to do that because those are extremely weak signals coming. So we have not, but I do remember now an amateur in the Netherlands did. So an amateur, I forget what he had, but if you adjust the dials just right, you could pick that up.
Because 100 minus 150 is way on down there.
Yep.
I mean, typically, handheld maybe, on a good day is going to get -120 maybe. Yeah. But it was just amazed me that they could work with signals that weak.
Yeah.
And your 60-foot dish has to be able to work in that realm.
Yep. So in some aspects, we're really just getting started. We just kind of got operational and just getting started to see what can we really do and things like that. So anything else? I appreciate your attention. And like I said, DSES.science will answer all your questions. Yep.
Well, that was a wonderful thing. Interesting stuff. Anybody have anything else? If not, I guess we're adjourned. We'll see you in January.